So our next speaker is Michael Collier, who is actually going to be taking us, I think, to a different wavelength band, the Lunar Environment Heliophysics X-ray Imager. Michael?
Okay, so let me, here it is, I guess I could go there. Okay, great, and indeed, I am going to be a break in this talk from the other talks in this session. This is going to be a talk about heliophysics from the moon rather than astrophysics from the moon. And in particular, today I'm going to talk about LEXI, the Lunar Environment Heliospheric X-ray Imager. And LEXI is a wide field of view soft X-ray imager. And it was accepted as part of the CLPS, the Commercial Lunar Payload Services Program, to be a payload on lander 19D, which should be selected later this fall. Now, LEXI is led by Principal Investigator Brian Walsh, who's a professor at Boston University, and it includes 6 other institutions, NASA Goddard Space Flight Center, Johns Hopkins University, University of Kansas, the University of Alaska at Fairbanks, the University of Miami, and the University of Leicester in the UK. Now, LEXI will observe the solar wind magnetosphere interaction from the surface of the moon to address outstanding problems in heliophysics, such as the nature of a process called magnetic reconnection. Now, LEXI detects something called solar wind charge exchange, SWCX or SWCX for short, soft X-ray emission. To understand this phenomenon, the phenomenon of SWCX, we need to go back to the mid-1990s. And in the mid-1990s, the ROSAT spacecraft imaged Comet Yakutaki in soft X-rays. You can see that in the figure in the upper left on this slide. Now, X-rays are usually associated with very hot objects, and comets are not hot at all. They're balls of ice. So it was quite a surprise at the time when ROSAT detected unexpectedly large amounts of soft X-ray emission from Comet Yakutaki. Well, this mystery was eventually solved by Tom Cravens at the University of Kansas, who is on our LEXI team. Now, referring to the figure in the upper right, high charge state heavy ions in the solar wind, such as oxygen +8, interact with cometary neutral atoms and steal an electron, charge exchange. However, the heavy ion, after this charge exchange process occurs, is in an excited state. And when that excited state relaxes, soft X-rays, X-rays below about 1 keV, are emitted. And since then, many observations of comets have been made in soft X-rays. Okay, so that's, of course, interesting, but is solar wind charge exchange soft X-ray emission useful? Or is this just an interesting scientific curiosity? Now note that this emission occurs not just at comets, but the emission occurs everywhere in the heliosphere that solar wind encounters neutral gas. In particular, at Earth, the terrestrial exosphere extends beyond the magnetopause, which is the boundary at the edge of the magnetosphere through which all solar wind momentum and energy powering space weather must pass. So the solar wind interaction with Earth creates a soft X-ray signal. In fact, the X-ray signal from the solar wind interaction with the terrestrial exosphere is always present. The figure in the slide in the upper left shows the observed correlation between the solar wind flux and the soft X-ray intensity from the solar wind interaction with the exosphere. Note that the in situ solar wind observations are in blue in this plot, and the soft X-ray intensities are red. So during this time period, the soft X-ray observations actually provide a more complete record of the solar wind flux than the in situ solar wind measurements. Now, we understand solar wind charge exchange emission well enough to perform accurate simulations. So the lower images on this slide show simulations of the soft X-ray emission from the solar wind interaction with Earth. So we can easily identify features in the images, such as the bow shock and the cusps. But most importantly for our purposes, we can image the inner boundary of the emission, which is the magnetopause. Okay, well, that's also great, but why in the world would you want to image the magnetopause? What is the scientific motivation for imaging the magnetopause? Well, there are many reasons, and I refer you to the comprehensive paper by Siebeck et al. The DOI is shown at the top of this slide for pretty comprehensive discussions on the broad scientific motivation for soft X-ray imaging. However, to provide just one example, the process of magnetic reconnection is the major mode of transferring the energy that drives space weather from the solar wind into the magnetosphere. One aspect of magnetic reconnection that we do not fully understand is its temporal nature. Does this process, the process of magnetic reconnection, occur quickly, slowly, or does it occur in bursts? Because magnetic reconnection moves the location of the subsolar magnetopause inward, by determining the location of the magnetopause versus time using soft X-ray imaging, we can deduce the temporal nature of magnetic reconnection and solve this question.
Michael, 2-minute warning.
Okay, thank you kindly. So, motivated by the science return, our team started considering various platforms for soft X-ray imaging. One potential platform is the surface of the moon. This location has the advantage that it is far from the subsolar magnetopause, facilitating global imaging. The concept of doing this soft X-ray imaging from the surface of the moon actually goes back over a decade to the Vision for Space Exploration. At that time, NASA funded several concept studies through LSSO, the Lunar Sortie Science Opportunities Program. The idea here was that, like the Apollo Lunar Surface Experiments Package, or ALSAP, astronauts would place instruments, such as an X-ray imager, on the surface of the moon to take measurements. Our original LSSO concept is shown here in this slide in the figure in the upper right. Now, under the LSSO opportunity, we were able to mature the instrument concept to the point where we could actually build prototypes. And indeed, we built prototypes. Now, solar wind charge exchange soft X-ray emission had been observed by astrophysical telescopes designed to image distant angularly small objects. For magnetopause imaging, we needed a wide field of view soft X-ray imager, which we developed and flew as a piggyback on the diffuse X-ray emission from the local galaxy, or DXL sounding rocket, led by Massimiliano Galeazzi at the University of Florida. The soft X-ray imager prototype, which we called STORM, was launched from White Sands Missile Range on December 12, 2012, and it performed flawlessly in spite of its Black Brant rocket experiencing what they called, quote, serious thrust anomalies, end quote, resulting in a very rough ride. Because this was the first flight ever in space of a wide field of view soft X-ray imager, our team got an invited article in Review of Scientific Instruments, along with the cover of the journal, which you can see at the right here in this slide. Okay, so this is the final slide. Where are we currently with LEXI? Well, we're currently refurbishing our soft X-ray imager to go on CLPS Lander 19D, which is the non-polar lander, with a delivery date of December 2021. This is, of course, challenging given the pandemic, but as of now, we're on schedule. Some enhancements we're making to the LEXI instrument to improve its performance for this lunar application include adding baffles to increase the signal to noise, adding a sunshade to eliminate stray light, and adding a cover for dust mitigation. So in summary then, LEXI, the Lunar Environment Heliospheric X-ray imager, will land on the moon as part of the CLPS program and observe the solar wind magnetosphere interaction from the surface of the moon. So thank you very much.
Great, thanks, Michael. We don't have much time, but I'll just ask a really quick question. I was wondering, like, how long is the time period for this experiment? You know, will it have to survive the night on the moon, or is it a shorter time length than that?
Okay, that's a particularly good question. We do not intend to survive the night. We're not designing with the intention of surviving the night. So we will be taking data, while we're in sunlight.
Gotcha. Thanks.